Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 11 Calorimetry. We'll be discussing the topics heat capacity, specific heat capacity and its measurement. Hope you all are ready for this session. Let's begin. First, we need to understand what heat is. Before that, we need to know what internal energy is. When you consider a substance, we know that this substance is made up of many molecules. If you have a container, this container contains a gas and there are many gas molecules. These molecules are in random motion. They are continuously moving. They will be colliding with each other. They will be hitting the walls of the container. We have studied all this, right? So, since these molecules are in motion, it means that there is a velocity. The body is moving. When a body is moving, when a molecule is moving, we can say that it possesses a type of energy which is kinetic energy. Kinetic energy is the energy possessed by a body due to its motion. Okay, therefore these molecules have kinetic energy. Now when you consider two molecules, there will be an attractive force or a repulsive force between them. Okay, so this force of attraction is due to the possessing of potential energy. The molecules will possess potential energy due to which there is a force of attraction. So the body has a potential energy. The molecules have potential energy as well. Okay, now we can define what internal energy is. The sum of potential energy and kinetic energy of a molecule is called internal energy. As we said, this molecule, if you take any one molecule, the molecule possesses potential energy as well as kinetic energy. Potential energy due to its force of attraction and kinetic energy due to its motion. Okay, so this sum of potential energy and kinetic energy will give you its internal energy. Now, we need to know what thermal energy is. The total internal energy. We have said this is one molecule. This molecule will be having an internal energy. Next molecule will have an internal energy. Next molecule will have an internal energy. So, the total internal energy of all molecules of a substance is called its thermal energy. So, understood what thermal energy and internal energy is? Now we can understand what heat is. Heat, for example, if you have two bodies, one is hot and the other one is cold. Okay, which body will be having more internal energy? Now if you take steam, steam is hot and ice is cold. Okay, in case of steam, you know that the molecules will be free to move. They are moving more. Motion will be more. Therefore, there will be more internal energy. Okay, so the hot body will be having more internal energy compared to the cold body. Now, when heat flows, that is, when these two bodies are kept in contact, what happens is this internal energy will flow. That is, the internal energy of the hot body will decrease and the internal energy of cold body will increase. Okay, when they are kept in contact, internal energy of hot body is going to decrease and that of the cold body will increase. So, there is some energy transfer happening and the energy which is getting transferred from the hot body to the cold body is called heat. Okay, so here you can see there is a flow of heat. There is a flow of energy and heat is a form of energy. When we have studied about different forms of energy, we have studied about heat energy. Okay, therefore we can define heat as a form of energy which flows from a hot body to a cold body when they are kept in contact. Bringing a hot body and cold body together, there is a energy which flows from hot to cold body and this energy is called heat energy. Okay, now in order to measure how much heat energy is there, okay, we can measure it using calorimetry. So, calorimetry is the measurement of the quantity of heat. The quantity of heat is measured by calorimetry. Clear? Now, what is the unit of heat? We said heat is a form of energy. We know that the energy, unit of energy is joules. Therefore, when you take the SI unit of heat is also joules. Okay, the SI unit is joules, but we have other units as well. The first is a calorie. 1 calorie. Okay, calorie is a unit of heat. Okay, 1 calorie, it is the quantity of heat that is required to raise the temperature of 1 gram of water through 1 degree Celsius. If you take 1 gram of water and change the temperature through 1 degree Celsius, you get 1 calorie of heat. Clear? So this is not a precise definition. The more precise definition is when 1 calorie is the heat energy that is required to raise the temperature of 1 gram of water. Again, 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So this is a more precise definition of calorie. Okay. So you got one unit which is the SI unit and commonly used unit which is calorie. Okay. This is a smaller unit. Now we have a bigger unit. In case of weight, you will be taking gram and kilogram. In case of length, millimeter, centimeter, kilometer, meter. There are different units. So this kilometer is a bigger unit, millimeter is a smaller unit. Similarly, here again you have a bigger unit and calorie is a smaller unit. So the bigger unit is kilocalorie. Okay. Before that, what is calorie? How is calorie and joules related? 1 calorie will be equal to 4.186 joules or approximately equal to 4.2 joules. So this is what 1 calorie is, the relation between 1 calorie and 1 joules. Now if you have to convert 1 calorie to joules, what will be done? 1 calorie into 4.186 joules. If you have 2 calories, okay, 2 calories. How much joules? If it is a question, you have to find how much joules is 2 calories. Then you will have to find 2 into 4.2 joules, which is equal to 8.4 joules. If it is 3 calories, it will be equal to 3 into 4.2. 3 into 4.2, which is equal to 12.6 joules. So this is how you can convert. Now the reverse conversion, that is joules to calories. How can it be done? 1 joule will then be equal to 1 by 4.2 calories. Okay. So this is how the reverse conversion can be done. Now kilocalorie. 1 kilocalorie is the heat energy that is required to raise the temperature of 1 kilogram. Here it is 1 gram. When it comes to kilocalorie, it is 1 kilogram of water. You will be taking 1 kilogram of water and rising its temperature from 14.5 degrees Celsius to 15.5 degrees Celsius. So got the units of heat. You have the SI unit and the commonly used units. How is calorie, kilocalorie and joules related now? We have said that 1 kilocalorie will be equal to, if 1 kilogram is 1000 grams and 1 kilometer is 1000 meters, then what is 1 kilocalorie? 1 kilocalorie will be equal to 1000 calories. Okay, 1000 calories. We know that 1 calorie is equal to 4.2 joules. Okay, so then what is 1000 calories? 1000 into 4.2 joules, which is 4200 joules. Okay, therefore 1 kilocalorie will be equal to 4200 joules. So this is the relation between kilocalorie and joules. Okay. Concept of temperature. Where have you used this word temperature? From your childhood, you have been hearing this word temperature. When you get a fever, doctor will be checking the temperature using a thermometer. So there you have heard this word temperature. Now what is temperature? We know that when you have two bodies in contact, that is a hot body and a cold body, what happens? When they are in contact, heat energy flows from the hot body to cold body. That is, a body which gives off heat is called a hot body and the body which gains heat is called cold body. So when this cold body gains heat, what is happening? The molecule starts vibrating. Okay. Due to this vibration, the temperature or the heat energy in it is increasing. Okay. So we can define temperature now. Okay. Temperature, it determines the flow of heat. In which direction heat is flowing. As we said here, it is from hot to cold body. Okay. When two bodies of different temperature are placed in contact. Okay. If both the bodies are at same temperature. For example, you have two bodies. Let's say both of these are at same temperature. 30 degrees Celsius, 30 degrees Celsius. Okay. Does heat energy flow in this case in any direction? No, right? There is no flow of heat energy because both the bodies are at same temperature. Now, this doesn't mean the thermal energy in them is also same. Okay, since the temperature is same, thermal energy, it is not necessary that thermal energy of both these bodies are also same, because thermal energy may depend on the mass, temperature and the material also. Okay, the amount of heat energy contained in a body depends on mass, temperature and the material of body. Understood? Got the concept of temperature? What is temperature? A simple definition is temperature, it is the degree of hotness or coldness of an object. How hot it is or how cold it is. Okay, the degree of hotness or coldness of a body is called temperature. What are the units of temperature? We have studied the units of heat, now units of temperature. The SI unit of temperature is Kelvin. There are two other units. One is Kelvin, second is degree Celsius and the next is degree Fahrenheit. Okay, here we don't have to study about Fahrenheit, we'll just study about what is Kelvin and what is degree Celsius and their interconversion. Okay, to find temperature in Kelvin, what you have to do is, if you know the temperature in degree Celsius, you just need to add 273.15 to it. Okay, on adding 273.15 or just 273 to degree Celsius, you will be getting temperature in Kelvin. For example, let's see how much Kelvin you get if you have a temperature given 25 degrees Celsius. 25 degrees Celsius plus 273. Okay, it is not necessary you always take 273.15, just 273 is enough. How much do we get? 273 plus 25, which is 298. Okay, so 298 Kelvin. 25 degrees Celsius is equal to 298 Kelvin. Okay, now what is 23 degrees Celsius then? 23 plus 273. Okay, 23 plus 273, you will be getting 296 Kelvin. Okay, next, if you need to find 27 degrees Celsius. What is 27 degrees Celsius? 27 plus 273, which is equal to 300 Kelvin. Now you have to remember one thing. Degree Celsius temperature can be having negative values, but never Kelvin goes to negative. Okay, so 0 Kelvin is possible, but not negative values of Kelvin. Okay, negative degree Celsius is possible. Now what is 0 Kelvin? How to convert Kelvin to degrees Celsius? As we said, T Kelvin is equal to degree Celsius plus 273.15. Then we will be having degree Celsius is equal to T Kelvin, where T is the temperature, minus 273. Okay, if it is 0 Kelvin, then degree Celsius will be equal to 0 minus 273, which is minus 273 degree Celsius. 0 Kelvin is equal to minus 273 degrees Celsius. Okay, so this temperature is called absolute zero. Okay, absolute zero. That is, at this temperature, if you take a substance, the molecule ceases its motion. The molecule is not in motion. And this is absolute zero. Now we can define absolute zero. The zero of the Kelvin scale is the temperature at which the molecular motion ceases. It is equal to minus 273 degree Celsius. Okay. Now when you take temperature difference, for example, 298 Kelvin and 295 Kelvin. What is the difference in temperature? 298 Kelvin minus 295 Kelvin. You will be getting 3 Kelvin. Okay. Now what is 298 Kelvin in degree Celsius? 298 Kelvin will be equal to 298 minus 273, which is 25 degrees Celsius. Okay, 25 degrees Celsius minus 295 Kelvins in degree Celsius, 295 Kelvin minus 273, which is equal to 22 degrees Celsius. 22 degrees Celsius. What are you getting? 25 degrees Celsius minus 22 degrees Celsius will be 3 degrees Celsius. Okay, so if you are using Kelvin scale or degree Celsius scale, this temperature difference value will be the same. Okay, here it is 298 Kelvin minus 295 Kelvin. We have converted into degrees Celsius. When you take the difference in temperature, it is 3 degrees Celsius. Same value you are getting, 3 Kelvin and 3 degrees Celsius. Therefore, you can write delta T Kelvin. Delta T means change in temperature with unit Kelvin will be equal to delta small t degrees Celsius. Okay, where small t is the temperatures in degrees Celsius and capital T is the temperature in Kelvin, in the units Kelvin. Okay, so the temperature difference when taken in degrees Celsius or Kelvin, you will be getting the same value. Clear? Factors affecting the quantity of heat absorbed to increase the temperature of a body. There are 3 factors. First, the mass of the body. Second, rise in temperature. And third, material of the substance. Okay. Mass of the body. Consider 2 bodies which is made up of same substance of masses M1 and M2. 2 different masses. Okay. The heat energy absorbed by both these bodies will be different even though the temperature rise is same. For example, let's say 1 degree Celsius is the rise in temperature. Okay. Here we have taken 1 kilogram of mass and here it is 2 kilogram of mass. In this case, the first case, to raise through 1 degree Celsius, the heat energy absorbed, let's say 1 kilocalorie. Okay. In this case, it will be 2 kilocalorie. To raise the temperature by 1 degree Celsius, if 2 bodies of the same substance of different masses are taken, then the heat energy absorbed by them will also be different. Here you can see when the mass increases, the heat energy is also increasing, which means the heat energy which is represented by Q is directly proportional to the mass of the body. When mass increases, heat energy increases. Now the second point, rise in temperature. Change in temperature. Okay, here you are considering 2 bodies of same mass. Let's say M mass. Here the temperature difference, let's say here it is 1 degree Celsius and in this case it is 2 degrees Celsius. Then the heat energy absorbed will also be different. For the body where the temperature difference is small, then the heat energy absorbed will also be small. Both of these are of same substance but same masses with different temperature rise. Okay, so here in this case, let's say 1 kilocalorie is the heat energy absorbed and here it is 2 kilocalorie heat energy absorbed. Again, you can see that the change in temperature, rise in temperature, when it increases, what is happening? The heat energy absorbed will also increase, which means heat energy is directly proportional to the rise in temperature or change in temperature. Now the third one, material of the substance. Here in this case, you are rising the temperature to the same degree Celsius. For example, 1 degree Celsius, 1 degree Celsius. Okay. Then the mass of the body, both are of equal masses. Okay. Substance is different. Okay, different substances. For example, 1 kg of water and 1 kg of copper. Okay, we have taken 1 kg of water and 1 kg of copper. In the case of water, the heat energy that is absorbed will be almost 10 times that absorbed by copper. So it also depends on which material or which substance we are using, material of the substance. So these are the 3 factors. Now we can say that the heat energy is directly proportional to mass. When mass increases, heat energy increases. Heat energy is directly proportional to rise in temperature. When rise in temperature increases, heat energy increases, which means heat energy directly proportional to mass and change in temperature. In order to remove this proportionality, we will be introducing a constant C m delta T. So this quantity C, the quantity which is introduced to remove the proportionality is called specific heat capacity. Okay, specific heat capacity of the substance. For each substance there will be a specific heat capacity. So this is the relation how you can find heat. Q is heat, M is mass, C is specific heat capacity which is a constant for a material and delta T is the rise or change in temperature. Clear? Let us differentiate between heat and temperature. The first point, you can write the definition of what heat is and what temperature is. What is heat? Heat is a form of energy which flows from a hot body to a cold body when they are kept in contact. Then what is temperature? Temperature is a quantity which determines the direction of flow, in which direction the heat is flowing on keeping the two bodies at different temperature in contact. Okay. Second point, you can write the SI unit. We know the SI unit of heat is joules and the SI unit of temperature is Kelvin. Now the third point, the amount of heat contained in a body depends on three factors. First is mass, then temperature and the substance of a body. Okay, depending on mass, depending on temperature and the substance which is being used, the heat which is contained in the body can change. Now what are the factors on which temperature depends? We know that if you have two substances, or in a substance we know that there are molecules. These molecules will be in random motion. Moving substances or moving molecules will be having kinetic energy. So in order to find the factor on which temperature depends, you need to take the kinetic energies average. Okay, the temperature of a body depends on the average kinetic energy of its molecules due to random motion. These molecules are in random motion. This moving molecules will be having kinetic energy. When you take the average of it, you will be getting temperature. That is, the temperature will depend on the average kinetic energy. Okay. Next point, heat is measured by the principle of calorimetry. Okay. We will be studying the principle of calorimetry later. So, in order to measure heat, you can use the principle of calorimetry. Now, how is temperature measured? We all know it is measured using a device called thermometer. Okay. Next, two bodies having same quantity of heat may differ in their temperature. Remember this point. For example, you are supplying same amount of heat. Okay. You are taking water and milk in two different vessels. Okay. And you are supplying the same amount of heat energy. But after 5 minutes, the temperature, it is not necessary that the temperature of water and the temperature of milk is always same. There will be difference. So, this is the point. Two bodies at same temperature may differ in their quantity of heat contained in them. This is with the case of an induction stove. You are supplying 1200 Kelvin temperature to water and to milk. Okay. Still, the heat energy that is gained by them in a particular time, let's say after 5 minutes, when you check, the heat energy may be different. Last point, when two bodies are placed in contact, the total amount of heat is equal to the sum of heat of individual bodies. If you have two bodies, let's say 10 joule and 5 joule, then when they are kept in contact, the total heat energy will be contained in the body will be 10 plus 5, 15 joules. Okay. Now, what about temperature? When two bodies at different temperatures are placed in contact, the resultant temperature is a temperature between the two temperatures. For example, if you have a body of 300 Kelvin kept with a body of 290 Kelvin, then combining these two substances, you will be getting the temperature of the substance lying between 300 Kelvin and 290 Kelvin, not above 300 Kelvin nor below 290 Kelvin. It should be a value lying between 290 Kelvin and 300 Kelvin. Okay, heat capacity. From our daily experience, we know that the amount of heat energy that is required to rise the temperature of different substances will be different. Even though you are raising the temperature, the same amount of temperature rise you have to bring, but still the amount of heat energy that is required is different. So, in order to understand this, every substance has a property called heat capacity. Okay, this heat capacity will help us to understand the rise in temperature. Now, how can you define heat capacity? The heat capacity of a body is the amount of heat energy required to rise the temperature by 1 degree Celsius or 1 Kelvin. 1 degree Celsius and 1 Kelvin, are they same? No. What does it mean? It is the difference in temperature. As we said, T Kelvin, change in temperature, delta T Kelvin is equal to delta small t degrees Celsius. Okay, the change difference will be the same. That is the same value for Kelvin and degree Celsius. So, this is how you can define heat capacity. That is, heat capacity is amount of heat energy supplied divided by the rise in temperature or change in temperature. For example, we say that for a body 500 or 5000 joules of heat energy is supplied and its temperature changes through 100 degrees Celsius. Okay, in that case, you can find heat capacity. What is heat capacity? Amount of heat energy required. Let's say heat energy is Q divided by rise in temperature, change in temperature, which is delta T. Heat capacity is represented using the letter C. Therefore, C is equal to Q divided by delta T. Here Q, the heat energy supplied is 5000 joules. Okay, Q is equal to 5000 joules and the change in temperature delta T will be 100 degrees Celsius. Okay, this is also equal to 100 Kelvin because this is change in temperature. Okay, 5000 divided by 100, which is 50. Okay, so 50 is the heat capacity and we'll be studying about the units of heat capacity. So understood, for a given substance, heat capacity will be a constant value. It won't be changing. Now the unit of heat capacity, we have studied what heat capacity is and other factors on which heat capacity depends. Heat capacity C is equal to amount of heat energy divided by change in temperature, Q divided by delta T. Okay, what is the unit of heat energy? Unit of heat energy is joules. So one possible unit is joule per change in temperature in degrees Celsius. Joule per degree Celsius, which is equal to joule degree Celsius inverse. Or when you are taking heat energy in joules and the rise in temperature in Kelvin, then joule per Kelvin, or that is joule Kelvin inverse. Okay, so these are the units. SI unit of heat capacity is joule per Kelvin or joule per degree Celsius. Okay, if you are taking heat energy in calories, then what do we get? Calories per degree Celsius or calorie degree Celsius inverse. Okay, if you are taking heat energy in calorie and temperature in Kelvin, temperature rise in Kelvin, then calorie Kelvin inverse. Okay, so this is also unit of heat capacity. Next, if you are taking heat energy in a bigger unit, that is kilocalorie. Kilocalorie divided by degree Celsius or kilocalorie degree Celsius inverse. Okay, heat energy in kilocalorie and temperature in Kelvin, then kilocalorie Kelvin inverse. Okay, these are the possible units of heat energy. Now let's see the conversion. Okay, what is 1 calorie? We know 1 calorie is equal to 4.2 joules. Okay, what about 1 calorie Kelvin inverse or 1 calorie degree Celsius inverse? You have to get it in joule per Kelvin or joule degree Celsius. Joule per degree Celsius or joule degree Celsius inverse or joule Kelvin inverse. How to convert this? Here we have 1 calorie. 1 calorie we know is 4.2 joules. Therefore, 1 calorie Kelvin inverse will be equal to 4.2 joules degree Celsius inverse or 4.2 joules Kelvin inverse. Okay. What about 1 kilocalorie Kelvin inverse? 1 kilocalorie Kelvin inverse will be equal to 1000 calories Kelvin inverse. And we know that 1 calorie is 4.2 joules. Therefore, this is equal to 4.2 into 1000 calorie Kelvin inverse to get it in joule per Kelvin. Okay, how much do we get? 4200 joules per Kelvin or joule Kelvin inverse. So, this is a conversion. Understood this? Okay, for example, if you have 40 joules Kelvin inverse. What does it mean? This means that 40 joules of heat energy is supplied in order to raise the temperature of the substance by 1 degree Celsius, or 40 joules of heat energy is required to raise the temperature by 1 Kelvin. Clear? So this is a unit of heat energy. Next, specific heat capacity. We understood what heat capacity is. This heat capacity, when you are considering for a unit mass of a substance, then we will be calling it specific heat capacity. So you can define specific heat capacity. Specific heat capacity of a substance is defined as the heat capacity per unit mass of a body of that substance. Okay, here this is very important for a unit mass. Okay, 1 gram of a substance or 1 kilogram of a substance, or specific heat capacity of a substance is the amount of heat energy required to rise the temperature of unit mass of that substance to 1 degree Celsius or 1 Kelvin. When we define heat capacity, there we didn't have this unit mass. It is the amount of heat energy that is required to rise the temperature by 1 degree Celsius or 1 Kelvin. When you add this unit mass, it becomes specific heat capacity represented by the small letter C. Okay, so we know heat capacity, capital C is equal to Q divided by delta T, where Q is the heat energy and delta T is the rise in temperature. Now we are considering for a unit mass, which means there will be the mass M. Okay, therefore specific heat capacity is equal to amount of heat energy supplied divided by mass into rise in temperature or into change in temperature. Clear? That is small c is equal to Q divided by M delta T. Or from this you can write heat energy Q is equal to Cm delta T. We have discussed this equation before. That is when we have studied the factors on which the heat energy depends. Okay, heat energy depends on mass and change in temperature or rise in temperature. Then the specific heat capacity of the material. Okay, 3 factors. First, it depends on mass. How is it dependent? Q directly proportional to M. When mass increases, heat energy also increases. Then Q directly proportional to delta T. When rise in temperature increases, Q value also increases. When the specific heat capacity of a particular substance is given, for that substance there will be a heat energy for a given mass and given rise in temperature. For different substances, the specific heat capacity will be different and hence heat energy, if you are taking the same mass and same change in temperature, since the specific heat capacity is different for different substances, heat energy will be different. So these are the 3 factors on which the heat energy of a substance depends. That is, depends on the material. Depends on specific heat capacity means it is the material of the substance on which heat energy is dependent. Okay. Now the unit of specific heat capacity, we have said that specific heat capacity C is equal to heat energy, amount of heat energy absorbed divided by mass into change in temperature. So what is the unit of heat energy? Unit of heat energy is joules divided by mass in kilogram and change in temperature in degree Celsius or in Kelvin. Okay, then this can be written as joule kilogram inverse degree Celsius inverse joule per kilogram Kelvin. If temperature is in Kelvin or rise in temperature is in Kelvin, then joule kilogram inverse Kelvin inverse is also a unit. So SI unit of specific heat capacity is joule per kilogram per Kelvin, which is represented as joule kilogram inverse Kelvin inverse, or joule per kilogram per degree Celsius joule kilogram inverse degree Celsius inverse. Okay, other units when heat energy is taken in calories. In that case, calorie divided by kilogram Kelvin, or calorie kilogram inverse Kelvin inverse. Calorie divided by kilogram degree Celsius, if temperature is in degree Celsius. Then you will be getting calories kilogram inverse degree Celsius inverse. That is changing the units, the possible units of heat, possible units of mass, possible units of temperature. Heat, you can have units joules, calories or kilocalories. Okay, for temperature, rise in temperature delta T, you can have units Kelvin and degree Celsius. For mass, you can have units gram and kilogram. If mass is taken in grams, in that case, you can have joule per gram per Kelvin, which is joule gram inverse Kelvin inverse. Okay, or joule per gram degree Celsius, joule gram inverse degree Celsius inverse. Okay, so these are the possible units. Clear? Now, if it is given that some 0.4 joule, kilogram inverse, Kelvin inverse is the specific heat capacity of copper. This is the specific heat capacity of copper. What does it mean? This means that the heat energy supplied is 0.4 joules to rise the temperature of 1 kilogram of copper through 1 degree Celsius or 1 Kelvin. Okay? To rise the temperature of 1 kilogram of copper to 1 degree Celsius or 1 Kelvin, the amount of heat energy is 0.4 joules. Then the heat capacity of the substance will be 0.4 joules, kilogram inverse, Kelvin inverse. Okay. Now, what is the relationship between specific heat capacity and heat capacity? How can you relate it? We have specific heat capacity C is equal to Q divided by M delta T. And the heat capacity capital C is equal to Q divided by delta T. Okay, Q by delta T is capital C. Okay, here we have Q divided by delta T. We can replace Q divided by delta T with this capital C, which means small c is equal to capital C divided by M, or capital C is equal to small c into M. What does this mean? Heat capacity is equal to specific heat capacity into mass. Okay, the relationship is heat capacity is equal to mass into specific heat capacity. Mass into specific heat capacity. Understood? So this is the relationship. Okay. Specific heat capacity of some common substances. You have to remember one point. Specific heat capacity is a characteristic property. It is a constant for a given substance. Okay, if you take some examples. For example, if you take copper and water. Specific heat capacity of copper is 0.4 joule gram inverse Kelvin inverse. And that of water is 4.2 joules gram inverse Kelvin inverse. That is, the specific heat capacity of water is greater than the specific heat capacity of copper. Copper we know is a good conductor. Okay, copper is a good conductor. What about water? Water is a bad conductor. So remember this point, for a good conductor of heat, it will be having low specific heat capacity. And for a bad conductor of heat, it will be having high specific heat capacity. Now if you take two substances, using the same burner, you are supplying equal amounts of heat energy, but there will be difference in the rise in temperature. Yes, this is because of the specific heat capacities. Since the specific heat capacities of the substances are different, the rise in temperature, some substances, or for example, if you take two substances, one substance it may be 10 degrees Celsius rise in temperature, for the other it may be 20 degrees Celsius, even though you are supplying the same amount of heat, say 50 joules of heat you are supplying, but the rise in temperature will be different because it depends on the specific heat capacity. Okay, remember this point. The substance with low specific heat capacity shows a rapid and high rise in temperature. That is, if you take a substance which is having a low specific heat capacity, then it will be having a rapid and high rise in the temperature will be rising very easily. Okay, very fast there will be a temperature rise. Delta T will be greater. Okay, but if you are taking a substance which is of very high specific heat capacity, in that case, it will be showing slow and small rise in temperature. It will be taking more time to change the temperature. Rise in temperature will be taking more time. Okay, so this is a difference. So for each substance, it will be different. Specific heat capacity will be different. Dependingly, the rise in temperature may also change even though the same amount of heat energy is supplied to the substances. Distinction between heat capacity and specific heat capacity. We understood the concept of heat capacity and what specific heat capacity is. So first, it is the amount of, as usual, just the definition, it is the amount of heat energy required to rise the temperature of entire body by 1 degree Celsius. Here it is entire body, mass. We are not speaking about the mass, how much it is, okay. The entire body to rise its temperature by 1 degree Celsius. When it comes to specific heat capacity, it is the amount of heat energy required to rise the temperature of unit mass. Unit mass means either 1 kilogram or 1 gram. of the body by 1 degree Celsius or 1 Kelvin. Okay, it is for unit mass. Here it is for the entire body. Next, it depends both on the nature of substance and the mass of the body. Okay, it depends on mass of the body and nature of the substance. More the mass of the body, more is the heat capacity. We have studied the relation heat capacity or heat energy Q is directly proportional to mass. Okay, so when mass increases, heat energy also increases. So there the heat capacity is also increasing. Now when you come to the case of specific heat capacity, it does not depend on the mass. Here mass dependent, here mass independent of the body, but it depends on the characteristic property of the substance of the body, how the body is, the material of substance it is dependent on. Next, heat capacity. How to find heat capacity? The relation between heat capacity and specific heat capacity. Mass into specific heat capacity will give you heat capacity. Capital C is equal to M into small c. Okay. Now just the reverse relation. Specific heat capacity. To get specific heat capacity here, keeping specific heat capacity, taking mass to the opposite side, we will be getting heat capacity by mass, which is capital C divided by M. Next is the SI unit. SI unit of heat capacity is Joule Kelvin inverse or Joule degree Celsius inverse. Okay. What about specific heat capacity? Its SI unit is Joule kilogram inverse. Here mass is also there. Kilogram inverse Kelvin inverse or Joule kilogram inverse degree Celsius inverse. Got it? So these are the differences between heat capacity and specific heat capacity. Principle of calorimetry or principle of method of mixtures. When we have done a differentiation between heat and temperature, we have said that heat is measured using the principle of calorimetry. Now let's see what is principle of calorimetry. When you have two bodies, a hot body and cold body, when they are kept in contact, what happens? Heat energy flows from the hot body to cold body. We know this. Okay. Now here, if there is no heat energy lost to the surrounding, then the heat energy that is lost by the first body or the hot body will always be equal to the heat energy that is gained by the cold body. So this is the principle of calorimetry. Statement is heat energy lost by hot body equal to heat energy gained by cold body. And remember, this principle is based on the law of conservation of energy. What is law of conservation of energy? Energy can neither be created nor be destroyed, but can only be changed or transformed from one form to another. Okay. So here the important condition is heat is not lost to the surrounding. Okay. So in this system, if heat is not lost to the surrounding, then the heat energy that is lost by the first body or the hot body will be equal to the heat energy gained by the cold body. Okay, for example, if you have two substances A and B. Okay, A is of mass M1, B is of mass M2. Temperature of A is T1, temperature of B is T2. Specific heat capacity of A is C1, specific heat capacity of B is C2. We are having a condition, A is the hot body and B is the cold body. Or you have two substances A and B and they are mixed together. Okay. Therefore, temperature T1 will be greater than T2 because A is the hot body. T1 greater than T2. Now, we know that from A to B, when you consider the system, heat energy is flowing. Yes. When heat energy is flowing, what happens to the temperature of A? Temperature of A is decreasing. Okay. Let it decrease and reach a value some T. Okay. Therefore, we can say that fall in temperature of A will be equal to, initially it was T1, it has changed to a smaller temperature T, small t. Okay, T1 minus T. Next, what is happening to B? The temperature is rising. Okay, therefore rise in temperature of B will be equal to, how much it is rising? So here it was T2, it is changing to T. Yes, therefore we'll be having T minus T2. Okay, now we got the temperature change. What about heat energy? Heat energy is lost by A. Heat energy lost by A will be equal to M1, C1 delta T. Here delta T is T1 minus T. T1 minus T. Okay. What about the heat energy? In case of cold body, it is gaining heat energy. Therefore, heat energy gained by B will be equal to M2C2 into T minus T2, change in temperature. Then according to the principle of calorimetry, we will be having heat energy lost by hot body, that is M1 C1 T1 minus T equal to heat energy gained by the cold body, that is M2 C2 T minus T2. Okay, M1 C1 T1 minus T is equal to M2 C2 T minus T2. Clear? So this is the principle of calorimetry. Okay. Calorimeter. Calorimeter is a cylindrical vessel which is used to measure the amount of heat gained or lost by a body when it is mixed with another body or substance. So this is how a calorimeter looks like. Here you will be using a thin sheet of copper to make the vessel. Copper is used. Two reasons why copper is used. One is copper is a good conductor. Okay. So to make the heat reach the contents inside the vessel, copper will be very helpful because it is a good conductor. It can easily conduct heat energy. Okay. Second reason is it has low specific heat capacity. Okay. Low specific heat capacity, and also then the content will be getting more heat. So heating of the content will become easier. Okay, these are the two reasons why copper is being used. So this vessel, it is then covered, an outer jacket for insulation purpose, an outer jacket is given which is made up of wood. A wooden jacket is given. Okay, so this is done in order to prevent conduction. Then you will be filling this empty space between this vessel, the copper vessel, and the wooden jacket with wool, or you can use cotton. So this is also in order to prevent the escape of heat energy. Okay, here the inner walls and the outer walls of this copper vessel, it is being painted properly. This is also done in order to prevent the loss of heat by radiation. Then you will be having a wooden lid. Okay, this is again made up of wood because wood is a poor conductor. It does not conduct heat. So wooden lid is being used in order to prevent convection, loss of heat by convection. Okay, in this wooden lid there will be two holes. Through one hole thermometer is passed, and through the other hole there is a stirrer passed. Okay, why is a stirrer used? Stirrer, as usual, it is being used for mixing the contents. If you are filling 2-3 substances, to mix these substances, a stirrer is being used. What about thermometer? Thermometer is being used in order to measure the temperature. Okay, so we have to be very careful that there should not be any loss of heat. Okay, from the contents, there should be no loss of heat. For that purpose, proper insulations are given, coating is given, and also this insulating substance, that is poor conductors of electricity, is being filled here. Clear? So this is what a calorimeter is, and a calorimeter will help us to measure the temperature of the mixture taken. Natural phenomenon and consequences of high specific heat capacity. We know that the specific heat capacity of water is very high. It is approximately 4,200 joules kilogram inverse Kelvin inverse. Okay, so the first one is the climate near the seashore is moderate. So when you consider a seashore, here you will be having the land and sea. Okay, now here it is water and here it is sand. Here you have to remember one thing, the specific heat capacity of water, C of water, is approximately 5 times the specific heat capacity of sand, which means the amount of heat energy required to raise the temperature of a given mass of water by a given temperature will be 5 times the amount of heat energy that is required to raise the temperature of sand by the same temperature, the same mass of sand by the same temperature. Okay, so here what happens is, during the daytime, due to sun, water and the sand will get heat up, but here the sand will be getting heated up very easily. So the cooling and heating of sand is very easy compared to water, because water is having a high specific heat capacity. So temperature change will take time. During this time, that is during the daytime, here there is a temperature difference, right? So temperature of the water and the temperature of land, of the sand will be different. So here what happens is breeze starts blowing, the cold breeze starts blowing from the sea to the land. Okay, sea to land, cold breeze will go. Okay, during the daytime. Now what about night time? Which will be more colder? Colder will be the sand. What is the reason? Because cooling of sand is easier compared to the cooling of water. So here again there is a temperature difference. Yes, due to this temperature difference, what happens? Cold breeze which is present in the sand or in the land, what happens to it? It starts blowing towards the sea. Okay, during the night time. So due to this reason, always in the seashore, the temperature will be a moderate temperature. There will be a balance in temperature. Clear? Hot water bottles are used for fermentations. That is to get relief from pain, you will be using these things. You may be used these things. Okay. What are this? We always know that this is always hot, right? And this heat helps our body to cure the pain. So why water is used? Why not petrol, diesel or some other liquids? Why we are using water? Because water is having a very high specific heat capacity. Okay. The specific heat capacity of water is 4200 joules kilogram inverse Kelvin inverse. It is very high compared to other liquids. So here what happens? The cooling of water takes longer time. Okay, and it can have a greater, that this higher temperature can be maintained for a longer time, which helps us to relieve the pain when these things are used. Okay, water is used as an effective coolant. A very simple example is, if you fill an earthen pot with water, morning when you touch, you can feel that cold effect. The water will become cool. Okay, similarly, when you spray water on the roof, what happens? It will be giving you a cooling effect. So water can be used as a coolant. Similarly, in case of machines, when you take the case of machines, the heated up part, by spraying water, you can lower the temperature. So this water is being used as a coolant in radiators, in generators, etc. In cold countries, water is used as reservoir for wine and juice bottles to avoid their freezing. So in cold countries, these wine and juice bottles can get frozen up easily. So here, before the water reaches its freezing point, what happens is, when you take a wine bottle, okay, it is kept in water. It is kept in water. Here what happens? We know that the specific heat capacity of water is high. Okay, so before it takes a longer time for water to reach its freezing point. Okay, so for a longer period of time, it can provide heat, or it can keep the bottle warmer. So for this reason, wine bottles and the juice bottles are kept in water. Farmers fill their field with water to protect the crops from frost. So you know that in plants or crops, there will be fine capillaries, their veins, okay, their water content is there. So during winter nights or cold nights, if the temperature goes below 0 degrees Celsius, what happens is, the water in these fine capillaries can get frozen up. Okay, then during the freezing, we know that when you compare water and ice, which has more volume? Ice has got more volume, the density is more, right? So here what happens is, due to this freezing, it can get burst. Okay, the veins can get burst and the plant and the crop will get destroyed. So in order to prevent this, we have to maintain a temperature which is not 0 degrees Celsius. Okay, so to do this, what is done is, water is sprayed on the crops. So in the field, by spraying water, what happens is, a temperature is maintained such that it doesn't reach 0 degrees Celsius. That surrounding temperature does not reach 0 degrees Celsius. All plants and animals have a high content of water in their bodies. We have heard that the human body, 70% of it is water. So mostly for animals and plants, about 80 to 90% is made up of water. So here we know that the specific heat capacity of water is very high. So this specific heat capacity of water helps to maintain a body temperature same in all seasons. When the season changes, our body temperature can be maintained same, because the presence of water content in our body, and water has a high specific heat capacity. Some examples of high and low heat capacities. So we are taking two cases. The first is a cooking pan and second is a calorimeter. So in case of a cooking pan, you can see that the base of this cooking pan will be thick. You know what is the reason? So it can retain more heat. That is, heat capacity will be more. If heat capacity is more for a greater time, heat can be retained in it, which helps the cooking easier. That is, for even if you off the stove, still for some time you can cook the food because of the heat that is retained. Okay, so here it is application is of high heat capacity, high specific heat capacity. Now the second case is with calorimeter. So in calorimeter, the vessel is made up of copper, a thin sheet of copper. So by making use of a thin sheet of copper, we know the copper's specific heat capacity is low. That is, the energy, the heat energy which is supplied will go into the content directly. That is, negligible heat is taken by the vessel. For this purpose, we are using the calorimeter to measure the heat energy. Okay, and so that the specific heat capacity should be low for the vessels. Vessel specific heat capacity should be low. By you making use of a vessel which is made up of a thin copper sheet, the specific heat capacity will be low and negligible heat is taken by the vessel. Okay. Let us take an example. Calculate the heat energy required to raise the temperature of 2 kg of water from 10 degrees Celsius to 50 degrees Celsius. Specific heat capacity of water is 4200 joules, kilogram inverse, Kelvin inverse. So here, given that the mass M is equal to 2 kg, then the change in temperature or rise in temperature will be equal to final temperature minus initial temperature. Here final temperature is 50 degrees Celsius minus initial temperature 10 degrees Celsius. Okay, which is equal to 40 degrees Celsius or 40 Kelvin. Okay, for change in temperature, both the units are possible. What else is given? The specific heat capacity C of water is given 4200 joules, kilogram inverse, Kelvin inverse. Okay, now we have to find the heat energy required. How to find heat energy then? Heat energy Q is equal to, we have an equation mc delta T. Just by substituting the value, you will be getting the final answer. Okay, so here Q is equal to mass 2 into C is 4200 into delta T. Delta T or change in temperature is 40. Okay, so this is equal to 8400 into 40, which is 3,36,000. Now what is the unit? Here specific heat capacity, the unit is joule, kilogram inverse, Kelvin inverse, which means the unit of heat energy will be joules. Okay, if you are expressing it in kilojoules, then 336 kilojoules, because 1 kilojoule is equal to 1000 joules. So this is a conversion. Okay, we got the heat energy required to rise the temperature, which is 3,36,000 joules. Clear? Second example. An electric heater of power 1000 watt raises the temperature of 5 kg of a liquid from 25 degrees Celsius to 31 degrees Celsius in 2 minutes. We have to calculate the heat capacity and the specific heat capacity of liquid. So what are the quantities that are given here? You have the power given. Power P is equal to 1000 watts rises the temperature of 5 kg of a liquid. 5 kg is the mass. Mass M is equal to 5 kilogram from 25 degrees Celsius to 31 degrees Celsius. Change in temperature, delta T is equal to 31 degrees Celsius minus 25 degrees Celsius, which is 6 degrees Celsius or 6 Kelvin. We got the change in temperature. In 2 minutes, time is given. Time T is equal to 2 minutes. So you cannot keep time in minutes when you have power in watts. You have to convert it. Convert it into seconds. 1 minute is equal to 60 seconds. Therefore, 2 minutes is 2 into 60, which is 120 seconds. Okay, 120 seconds. Here we have to find the heat capacity. How to find heat capacity? We know heat capacity is the equal to heat energy lost or heat energy gain divided by change in temperature. We need to find the energy first. There is a relation between energy and power. Yes. So using this we can find the heat energy. Okay. Energy is equal to power into time. So here the power is 1000 watts into time is 120 seconds, which is equal to 120,000 watt seconds or joules. Joules is a unit of energy. Or this can be written as 1.2 into 10 raised to 5 joules. Okay. So we got the energy, and this energy is the heat energy in this case. Q is equal to 1.2 into 10 raised to 5 joules. Now we can find the heat capacity. First, to find heat capacity, which is capital C. How to find heat capacity capital C? It is heat energy divided by change in temperature delta T, 1.2 into 10 raised to 5 divided by change in temperature delta T is equal to 6. Okay, divided by 6, which is equal to 12 into 10 raised to 4 divided by 6, and that is 2 into 10 raised to 4. Okay, 2 into 10 raised to 4. Now, what is the unit? Unit here, heat energy is in joules. Change in temperature, either you can take in Kelvin or degree Celsius. Joule Kelvin inverse. Okay, we got the heat capacity. Next, second part, we have to find specific heat capacity. We have a relation connecting specific heat capacity and heat capacity. Specific heat capacity, small c, is equal to heat capacity capital C divided by mass m. 2 into 10 raised to 4 divided by mass m is 5. This can be written as 20 into 10 raised to 3 divided by 5, which is 4 into 10 raised to 3. What is the unit of specific heat capacity? Joule, kilogram inverse, Kelvin inverse. You have to remember, here mass is in kilogram. If mass is in grams, then in the unit you will have to put gram inverse. Clear? Third example. What mass of a liquid A of specific heat capacity 0.84 joules gram inverse Kelvin inverse at a temperature of 40 degrees Celsius must be mixed with 100 grams of a liquid B of specific heat capacity to 0.1 joule gram inverse Kelvin inverse at 20 degrees Celsius so that the final temperature of mixture becomes 32 degrees Celsius. Okay, so final temperature of mixture is given. What else is given? What mass of a liquid A of specific heat capacity? Specific heat capacity of A is given. Ca is equal to 0.84 joule gram inverse Kelvin inverse. At the temperature 40 degrees Celsius must be mixed, which means the temperature of A is equal to 40 degrees Celsius with 100 grams of liquid B. 100 grams. So, mass of B is equal to 100 grams. Of specific heat capacity 2.1 joule gram inverse Kelvin inverse. Cb is equal to 2.1 joule gram inverse Kelvin inverse at 20 degrees Celsius. Tb, temperature of B, is equal to 20 degrees Celsius so that the final temperature of mixture becomes 32 degrees Celsius. So, final temperature we represent it as T. T is equal to 32 degrees Celsius. Okay, we have to find the mass of A. Okay, now according to the principle of calorimetry, we have a mathematical expression M1 C1 into T1 minus T is equal to M2 C2 into T minus T2. Okay, now put all the values. Here we have taken A and B. MA CA TA minus T is equal to MB CB T minus TB. Okay, put the values. MA we don't know. We have to find MA. Keep it as it is. CA. CA is 0.84. 0.84 into TA minus T. Here TA is 40 degrees Celsius. T is 32 degrees Celsius. 40 minus 32 equal to MB. Mass of B is 100 grams. 100 into CB. CB is 2.1. 2.1 into T minus TB. Here T is 32 degrees Celsius. TB is 20 degrees Celsius. 32 minus 20. That is MA into 0.84 into 40 minus 32 is 8 equal to 100 into 2.1 into 32 minus 20, which is equal to 12. Okay, we need to find MA, keeping MA on the left hand side and taking all other terms to the right hand side. 100 into 2.1 into 12 divided by 0.84 into 8. Cancelling, here we get 2, here 3, then 2.1 and 0.84 can be cancelled, which is 0.4. That is, we'll be getting 300 divided by 0.4 into 2, which is 0.8, or 3000 divided by 8, which is equal to 30 by 8. You will be getting 24. 24 3 times 60. In 60, you will be getting 7 times, okay, which is 56. 40. 40 by 8 is 5. 375. Okay, what is the unit? Here mass is in grams. 375 grams is the mass of liquid A. Okay, let us now do numericals from exercise 11A. So first question, by imparting heat to a body, its temperature rises by 15 degrees Celsius. What is the corresponding rise in temperature in Kelvin scale? What is the answer? Here delta T degrees Celsius is given. Change in temperature or rise in temperature is 15 degrees Celsius. We have to find what is the temperature in Kelvin. Delta T Kelvin. How to find? They will be same, right? Change in temperature, if the unit is degree Celsius or Kelvin, doesn't matter, the quantity or the magnitude will be same. Therefore, delta T will be equal to 15 Kelvin. This is the same. The magnitude will be the same even though the unit can be either degree Celsius or Kelvin, because this is a change in temperature. We have studied this before. When you take the difference of 300 Kelvin and 298 Kelvin, you will be getting 2 Kelvin. Okay, 300 Kelvin is 27 degrees Celsius and 298 Kelvin is 25 degrees Celsius. The difference will be 2 degrees Celsius. Okay, so the quantity or the magnitude is the same. Clear? Problem number 2. A piece of iron of mass 2 kg has a heat capacity of 966 joule per Kelvin. Find heat energy needed to warm it by 15 degrees Celsius, and second, its specific heat capacity in SI units. So given that we have mass of iron M is equal to 2 kilogram, specific heat capacity we have to find, and heat capacity is given capital C equal to 966 joule per Kelvin. So first part we have to find heat energy. How to find heat energy? Heat energy Q. How to find heat energy? We have a relation, specific heat capacity or heat capacity is equal to heat energy divided by change in temperature. Change in temperature is also given. Here we have to find the heat energy needed to warm it by 15 degrees Celsius. That is a temperature increase or rise in temperature is 15 degrees Celsius. Therefore, delta T is equal to 15 degrees Celsius or 15 Kelvin. Okay, change in temperature. Therefore, capital C is Q divided by delta T, which means Q is equal to capital C delta T. Okay, now put the value. C is 966 into delta T is 15, which is equal to 14,490 joules. Okay, so this is your heat energy. Heat energy to warm it by 15 degrees Celsius. Now the second part of the question, we have to find the specific heat capacity in SI unit. What is the SI unit of specific heat capacity? Joule kilogram inverse Kelvin inverse, or Joule kilogram inverse degree Celsius inverse. Okay, how to find specific heat capacity? You can use two formulas. The first one, we have Q is equal to MC delta T, where Q is heat energy, M is mass, C is specific heat capacity, and delta T is the rise in temperature, from which you will be having specific heat capacity C is equal to Q divided by M delta T. Okay, C is equal to Q divided by M delta T. Now, we also have a relation connecting specific heat capacity and heat capacity. Specific heat capacity C is equal to capital C divided by M. Q by delta T. Q by delta T will be your capital C. Okay, capital C by M. Do we know the value of capital C? Here capital C is given, right? Capital C is 966. So, C is equal to 966 divided by mass. Mass is 2 kg. 2, which is equal to 483 joule, kilogram inverse, Kelvin inverse. Okay, same answer you will be getting if you substitute these values. Heat energy Q we have determined, which is equal to 14490 divided by mass M. M is 2. And what about delta T? Delta T is 15. Okay, 14490 divided by 15, you will be getting the value 966. 966 divided by 2, you will be getting 483 joule, kilogram inverse, Kelvin inverse. Okay, any of these formula you can use. Problem number 3. 1300 joules of heat energy is applied to rise the temperature of 0.5 kg of lead from 20 degrees Celsius to 40 degrees Celsius. Calculate the specific heat capacity of lead. Here given that the heat energy Q is equal to 1300 joules. Then what else is given? Mass is given. Mass M is 0.5 kg. Change in temperature we can determine. Initially it is 20 degrees Celsius. It is being raised to 40 degrees Celsius. Therefore 40 degrees Celsius minus 20 degrees Celsius, which is equal to 20 degrees Celsius or 20 Kelvin. Okay. Here we have Q, M and delta T. We have to find specific heat capacity. We have Q is equal to MC delta T. Then C is equal to Q divided by M delta T. Okay, substitute the values. C is equal to Q. Q is 1300 divided by M. M is 0.5 into delta T is 20. Okay, so taking this 0 and this point can be removed. It becomes 1300 divided by 5 into 2. Okay, the 0 is used to remove this decimal mark. Okay, so 5 into 2 is 10. 1300 by 10, cancelling 0, we get 130. And the unit is joule, kilogram inverse, Kelvin inverse. Okay, specific heat capacity is 130 joule, kilogram inverse, Kelvin inverse. Clear? Problem 4. The temperature of 600 grams of cold water rises by 15 degrees Celsius when 300 grams of hot water at 50 degrees Celsius is added to it. What was the initial temperature of cold water? So here you have hot water and cold water. Hot water is added to cold water. Okay. So here what is the mass of hot water? We'll take the mass of hot water as M1, which is equal to 300 grams. Of hot water at 50 degrees Celsius. Temperature is given, therefore T1 is equal to 50 degrees Celsius. Now the temperature of 600 grams of cold water, which means M2 is equal to 600 grams, rises by 15 degrees Celsius, which means here T2 is not given, but the change in temperature delta T is given, where delta T will be equal to T minus T2. Okay, T minus T2, and here it is equal to 15 degrees Celsius. Okay, therefore T minus T2 is 15 degrees Celsius. Now we have to find the initial temperature of cold water, which means we have to find the value of T2. According to the principle of calorimetry, we have M1 C1 into T1 minus T is equal to M2 C2 into T minus T2. Okay, but here we don't know what C1 and C2 is. Given that both the substances are water, which means their specific heat capacity will be same. Yes, the value will be same. Therefore, they can be removed from both the sides. They are equal value. What is M1? Here M1 is 300 into T1 minus T. T1 is 50. 50 minus T is equal to M2. Here M2 is 600 into T minus T2 value we know, which is 15 into 50. Okay, that is 50 minus T is equal to 600 into 15 divided by 300. Cancelling, here we get 2. 2 into 15, 30. 50 minus t is equal to 30. Taking this 30 to the opposite side and t to the opposite side. Here it is minus t, it becomes plus t. 30 becomes minus 30. Okay, 50 minus 30 is equal to t, which means t is equal to 20 degrees Celsius. Okay, T is 20 degrees Celsius. We have T minus T2 is equal to 15 degrees Celsius. Yes, so T is 20 degrees Celsius. 20 degrees Celsius minus T2 is 15 degrees Celsius. Taking this T2 to the opposite side, we get T2 is equal to 20 degrees Celsius minus 15 degrees Celsius, which is 5 degrees Celsius. Initial temperature of the cold water is equal to 5 degrees Celsius. Clear? That's all for today. In today's class, we have discussed about heat and temperature, the concepts of heat and temperature. We have differentiated between heat and temperature. We have studied their units. We discussed about heat capacity and specific heat capacity, the relation between them, and we have also solved problems related to it. We have studied what calorimetry is, what is calorimeter, and also we have studied applications. Where does this get applied? Okay, hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learno Hub. Learno Hub free hai par best hai.